Orbital mechanics, a historical perspective. What actually is an orbit? It's a great question. If there are at least two, quote, bodies in space, orbit is the motion they have around each other. Typically, one is much larger than the other, but that's not always the case. Pluto and its moon, Charon, are a good example of this. That moon is a large moon in comparison to the size of Pluto. In most cases, though, the smaller object orbits the larger, and the larger object is often thought of as being fixed in space. What actually is a satellite? We usually think of this as being a human-made object that orbits Earth. Really, it's any object orbiting another body in space. So the Earth itself is a satellite of the Sun, just like the Moon is a satellite of the Earth. Let's take orbital mechanics all the way back to the times of ancient Greece. Aristotle is well known for studying the motion of planets, as he and his peers had a keen interest in how the heavens moved in our night sky. A geocentric point of view was common during this time, and all objects in space were thought to move around the Earth. It's pretty conceited, right? Well, it wasn't until this man, Copernicus, that we had a heliocentric point of view. He theorized this, though he did first think that the motion of their orbits was completely circular. And it wasn't until he started taking accurate measurements of them that he realized this wasn't correct. It didn't help that the church found this kind of thinking and theorizing to be heresy. After all, humankind must be the center of the universe. Tycho Brahe. You probably haven't heard much about him before. Here's the deal. A few years after Copernicus left the scene, he died. Tycho Brahe was born. Now, Brahe was incredibly interested in what Copernicus was doing and what his discoveries meant. As Brahe began investigating this information that Copernicus began to gather, he found minor tweaks that could be made to the methods of collection. So he is known for his extensive work in accurately measuring the planetary motion of his time. Still, the circular orbits didn't make sense. Something was wrong with that. About the time that Brahe's work became more popular and publicized was about the time this guy was born, Johannes Kepler. He wound up working with Brahe in Tycho's later years and expanded upon his work, proposing that planetary orbits were not circular at all, but rather elliptical. This breakthrough answered so many questions, and the laws of orbital motion he proposed and the Keplerian elements we use today were named after him. These still describe the orbital motions of celestial bodies as we think of them now. This guy, Robert Hooke, came on the scene after Kepler and was a rival to Sir Isaac Newton. Now, Robert Hooke was a great man. He came up with some really wonderful things, but one of the most fascinating things about his history as it pertains to orbital mechanics is that his infatuation with debating Newton is what led to Newton writing the Principia. And then there was Sir Isaac Newton. There is so much written about the history of Isaac Newton, you could fill numerous books. And people have. He was able to take Kepler's work and deduce the inverse square law that helps to explain how the attractive force works. Newton took his love of astronomy and math and proposed the theory of universal gravitation. He created the greatest scientific book ever written, called the Principia. This is where he posits his three laws of motion, and of course provides all the mathematical evidence to prove them. It's reported that his conflict with his peers, like Hooke, drove him mad until he was able to prove to them, and of course himself and all of us, with this book, that his ideas and theories were accurate. In conclusion, these are the shoulders on the giants of which we stand. They go back to ancient Greek, when we thought everything revolved around us, to deducing the math and concepts that we still use to describe motion and physics on a macro scale. Without them, we would have never made it into the air, out of the atmosphere, and land objects and people on other planets, because they knew how to build off of each other's work, find a respect for one another eventually, and be keen on debating theories and ideas. We're able to launch rockets, predict with certainty where objects will land when thrown, and understand the motion of those objects that are all around us and in space.